all I got for y'all today. So Dr. Larry, I'm going to go ahead and let you take it away.
Okay, thanks a lot.
Yeah.
Okay, and thank you guys for being here too. It's a real treat to finally get out and to start getting among our peers a little bit more, especially after this last year when we've been shut down so long. And also the MD Expo staff, they've been really over this past year at having programs like this to help get us out and kind of look at these conferences as kind of a form of opportunity to kind of recharge our professional batteries in a sense of hanging around with like-minded geeks, you know, and just sharing our stuff back and forth and just, you know, seeing things that are going on here. So anyway, what I want to kind of share with you today is kind of approaching probably some bit of blasphemy in that I want to really get you to think about and challenge our literally decades old legacy of measuring leakage currents. We've been doing this now 40, 50 years or so. And if you've ever been out there in the trenches, which I was in my early days out there measuring these things, and little by little, I started to ask myself, what am I doing this for? You know, there's so many other things to be doing out there. And especially where you guys are at now, you've got a ton of things to be doing rather than out there doing these leakage current measurements. So I guess what I'm asking you to kind of try to do, if you can, is try to decouple these measurements from electrical safety. It's become over the years kind of inextricably connected with safety. And anything that challenges safety is, again, almost blasphemous in that we cannot challenge safety, which we're not advocating that by any means at all. It's just this particular practice we have of measuring the leakage currents. We're still talking, we're not going to challenge at all or diminish the need for checking line cords, plug caps, strain relief. You know, these things get banged up and shoot up all the time. So we're still going to continue with that. But it's these leakage current measurements that I want to particularly focus on. And hopefully by the time we get done here, you'll see that there are 5 necessary conditions that have to be present before we're going to shock anybody. And all of these concepts we're going through here are based on established AC circuit principles, engineering scientific methods and concepts that are frankly not up for debate. They're all based on what we'll see are basically immutable laws of nature and science as to where these currents come from, how they affect the body, and what really needs to be necessary before we have any kind of risk at all. So we'll kind of go through some of these things, especially some of the stuff in the beginning. It may have been years or even more before you had some of this stuff in school. So some of these concepts might be somewhat familiar. And if they are, you can kind of bear with me a little bit. And if they start to get too painful, you know, some of these things might bring up old bile from your school days on, oh God, I hated that crap. You know, but we have to review some of that in order to get the foundation down about why we can get rid of doing these tests. So fundamentally, this all started, we have Michael Faraday to thank for this, but the fundamental concept of where and why we get alternating currents available from our wall outlets all ultimately comes down to the basic relationship he developed, you know, a couple hundred years ago. And all it fundamentally says is that if we have a coil of wire moving in the presence of a magnetic field, we can get a voltage across the terminals of that coil. That's all that expression basically says. That fundamentally, we could have a stationary magnet like we have here, and we rotate a coil, we'll get a voltage. Or we could have a stationary coil, we move the magnet, we'll get a voltage. That's all that DT stuff is changing magnetic fields. But that's the fundamental principle that gives rise to where we get AC from. And again, anytime you see something that's qualified as a law, that means it's not up for debate. It's not an opinion. It's not something we could, well, maybe we do it, maybe it, no. It's a law of the universe, not up for change. And that's what makes it so elegant, is that they don't become obsolete as this stuff goes on. Okay, so fundamentally, and
when we connect an AC generator to a closed cable, a current will be able to flow through this cable and the direct.
But you know, the generator at the place of the generator, why it's called alternating is because literally the electrons are moving alternately back and forth in the conductor, and that gives rise to our sinusoidal voltage that we have at our wall outlets, a changing polarity signal. So it goes positive and it goes negative, obviously, alternate. So alternating voltages produce alternating currents. And this is where some of this angst may be coming from your old school days. And we don't have to get at all worried about the symbols and the some of the symbology here, but just appreciate the concept of that it's this rotating coil that gives rise to this alternating signal. All of this stuff is ultimately critical in appreciating why we don't need leakage currents. It's all where it all comes from. So as this coil is moving around here, we get a peak value, goes to 0, negative peak, and it just continues to do that. In that period here, the time it takes to complete one full cycle is a function of the power, what happens at our power plants. So the generators at the power plant, typically steam driven, produced by heat from nuclear, coal, wind, hydro. The speed of that turbine is it's fixed at 3,600 RPMs, and that's what gives rise to our 60 hertz frequency of our electrical power. So it's all based on the speed of that turbine. All of this radians per second stuff, that's just mechanical gearhead terminology for the speed. It's another way of expressing speed, revolutions per minute, radians per second. So the reciprocal of that frequency gives us the period. So that period, the time it takes to complete one full cycle, 16 milliseconds. You remember your oscilloscope days? You probably don't use them for anything anymore, do you? You might have stuck in the closet somewhere. But you remember the beauty of the oscilloscope is that it allows us to measure amplitude of any signal as well as the period. So it's a perfect tool for characterizing and describing fully the nature of an alternating signal, or any signal for that matter. So here we have, if the scope is set up accordingly, we have 0.2 volts peak value. And if we know the horizontal sensitivity here, we can determine the period, the time to go one complete cycle, in this case 200 microseconds. You can't see it there, but 1 over 200, so it says that's a 5 kilohertz waveform. So that describes the alternating, completely describes the signal. And if you remember way back, and this is what students start to gag on, we have the more complicated terms for expressing how we would define that voltage signal in terms of trig functions and pi's and all of that kind of. We don't think like that in the real world, but that's in the engineering scientific world. That type of an expression is what fully describes that waveform. So what we saw here on the oscilloscope, that waveform, physically, graphically, is equal to that. Or whatever that's. Again, you don't deal with that kind of complexity in the world data, the normal world, but it completely describes the nature of that signal. Fortunately, we have a simpler shorthand method, which we refer to as the RMS value of the waveform. Root mean square RMS value, much simpler, very straightforward, more straightforward. And this is what our multimeters measure. So you have an AC multimeter, AC milliamp meter. What you're displaying here is current and voltages in RMS values. Your safety analyzers display microamps in RMS microamperes. And all that is sometimes it's also called the effective value. And what that simply means is that if we had a water bath here with a heater element in it, and we connected a DC voltage source to it, the water would heat up, right? Just like a coffee water heater would heat up to some value. The amount of AC that produces the same heating effect is the RMS value. But we also call it the effective value, that produces the same heating effect. So 120 volts nominally that we refer to our outlet voltage there, that's an RMS value. 120 volts of DC would produce the same heating effect in that same volume of water. That's all RMS means. So you can think of RMS also as an equivalent DC voltage associated with our alternating waveform. If you knew the peak value of the AC waveform, multiply it times 0.707, you get RMS. If you knew the RMS, times square root of 2, you get a peak. And we don't normally have to do those kinds of things, because we just simply work in our world in RMS values. I don't know if you've heard of any of the neurally controlled prosthetics that we have increasingly more of. We have artificial limbs that we can put electrodes on the chest, and subjects or patients can learn how to control artificial arms through their EMG signals picked up off the chest. those EMG signals ultimately are converted to RMS values to drive the motors and the actuators in those devices. RMS. So again, you want to be ultra geeky about it. Instead of an equivalent way of expressing 120 volts RMS at 60 hertz is 170 sine 370. Even without talking like that, then you kick it out of the room right there. And that's technically what the equivalent value is. See, just the RMS value by itself tells us the magnitude, but it doesn't tell anything about the frequency. So this expression here gives us a more complete information about it. So any periodic waveform we can get an RMS value from. In fact, there's chips, integrated circuit chips that are in our multimeters. They're RMS converters. You put in some periodic waveform and the output will be a DC signal corresponding to RMS value. And we actually, the way we do it electronically and mathematically is just the opposite. So first we square the waveform, gets rid of the negative pieces, then we take an average or a mean, and then take the square root of it to get back to our original. This is all going to hopefully come together and make some more sense as we go on here. Okay, but fundamentally, this is what we have in our residential areas where the incoming power typically is coming in at residentially around 14 kV, 1,000 volts. And you'll see these big transformers, sometimes we call them pole pigs, hanging off the pole out there. These are simply what we're now going to step down that 14,000 volts residentially to typically 240 nominally or so. And that's what's going to come into our houses. Okay. How the transformers work, this is also all connected here, is also predicated on Faraday's law, induction. So we've got an alternating current voltage source here, producing an alternating magnetic field. So that's that dφ/dt. This changing magnetic field here is cutting across another coil, the secondary coil in the transformer, and that induces a voltage out here on the secondary. So it's that alternating current that produces an alternating, you see the polarity changes, gives us a corresponding induced voltage. Again, from your basic, somewhere along you had a course on this stuff back in the days. Anyway, this is the fundamental of a transformer. It's a passive device also. And depending on simply the number of turns of wire, that's all N is here. P is on the primary, N is secondary. Simply the number of turns of wire on that core determines whether we step up or step down voltages and step down currents. So it's a very fundamental, very basic device, works great. This little feed here shows the flux, the magnetic flux lines that literally are circulating in the transformer, alternating. And also ideally, the power in should be equal to the power out of the transformer. And the power is, again, just RMS current times RMS voltage is power in watts. Ideally, it should be equal, but as you know, nothing is ideal. And one of the reasons why these get warm, you've all felt the warmth of wall warmth. Any transformer, you'll see if it gets warm, it's because of losses. There's 3 different kinds of losses in the transformer, and that's what gives rise to the output not being equal to the input. In your many of our ORs where we have isolated power systems still in place, another topic we could get into, the turns are the same. So we put 120 volts in, we get 120. Okay. How all of this power is ultimately distributed in our environments is fundamentally as we have shown here, where this in our residential environment, we've got our 220 coming in. So the 3 big conductors coming into our house, we have 120 on either side of the neutral, and that comes into a circuit breaker panel. And the key thing here with all of this that we need to, we hopefully know already, but is right where the power comes into our environments. Ground and neutral are bonded together, physically bonded together, physically, electrically, mechanically bonded together. And that connection also is connected to the physical dirt. Somewhere outside, you probably can't see it anymore in your own homes, but there's a conductor coming out of your circuit breaker panel and going into two typically, 8-foot rods or so separated apart buried into the physical dirt. And the point of all of that is why we refer to it as ground. In the UK, it's like earth, they call it earth, because it's literally the earth. But the point is that now our 120 volts, hot, small blade here, is electrically referenced to the physical earth, to dirt. And that becomes a critical issue, as we will see going forward. But that's the fundamental nature behind how this stuff is wired. I don't know if you've ever had any issues like with intermittent problems. Sometimes you're trying to troubleshoot systems and you get these flaky intermittent things going on. And a long time ago when I was in the hospital, I actually made up I heard about somebody talking about this once, measuring the ground neutral voltage, the potential between neutral and ground. Theoretically, ideally, that should be zero, right? If you have a ground and a neutral connected together, if they are indeed bonded at one point, the voltage across two pieces of wire should be zero or very close to zero. And if you start to measure something in the 2, 3, 4 volts or so, that can suggest that you've got some potential issues with that earth-ground connection, and that can give rise to some really flaky behavior in some systems. So I had a little pigtail made up that I plugged into the multimeter, just two bananas plugs coming off of the ground and a neutral, and just something I just would routinely check just to verify that. Because sometimes after you've had multiple renovations in the space, you think things have been done properly, but sometimes you can get whacked. Okay. This also gives rise to the grounded outlet. I only found out about this maybe 10 years ago. I graduated from Milwaukee School of Engineering, and I'm currently teaching there for the last 20-some years ago, before being in hospitals for 20-some years. I just found out some years ago that a student at MSU invented this outlet. A student in 1928 invented the currently 3-prong outlet. And the urban legend is that he lived in an apartment building and his landlord had a cat that was getting shocked every time it backed into some box fan that the landlord had. So he just, what if I ground that metal case on the fan? Cat didn't get shot. So I can't imagine, if he got a penny for every outlet like that. I don't know what happened to the guy, but I thought it was pretty wild. We're the geek factory, the school that I'm at. It's a real nut house in a lot of ways. Really. In fact, every fall you can just tell. The sophomores, they cut the freshmen. They're all eager beavers and they're all chomping at the bits and ready to go. And if you just look across the sea of them, you can say, yep. And I hate the stereotype, but I don't mean it in a derogatory way in any way at all. But it's like our software engineers, they're out there. We're kind of geeky and naughty, but those guys are out in the cosmos somewhere. But that's just kind of how we were born. I think that's why we do what we do. What we've also been really, really diligent with, and it's a good thing, is we've been really faithful. There used to be codes and standards out there on verifying the continuity, the ohmic resistance between the case of our devices and the ground pin. So our safety analyzers do all of this for us and measure it. And we want that resistance to be less than a half an ohm, 150 milliohm. We want it to be low. And that's what it should be, obviously, because it's just a piece of wire. If we've got good mechanical contacts in the plug, good contacts on the case, that's generally not an issue. What we haven't been as diligent about, however, because we kind of think, well, facilities are supposed to deal with it, is what is the ohmic resistance between the ground pin and the socket? Maybe in our old homes, if you've got a pin and a socket, if it's a real sloppy connection, what happens to your resistance? Your ohmic resistance can go up, or it could be non-existent if it's real bad. If you've ever unplugged something from the wall and the plug is warm, ding, 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 either you have some loose connections in the plug, Or you could have a real sloppy connection here with the power and the neutral. If you remember from your fundamentals, power in watts is I squared R, the current squared times the voltage. So if you had, say, a 10 amp pack of some sort, 10 amps, maybe 120 watt, 1200 watt appliance of some sort, 10 amps squared times an ohm, or even a half an ohm, just say a half an ohm of resistance, 100 times 0.5, you could have 50 watts of power being dissipated at the plug, receptacle interface. That's why they get warm. So we want the ohmic resistance between those plugs and the socket to be as reasonably low as we can. That's why we have the hospital grade receptacles. That's not just a marketing thing. In the old days, I actually took them apart. You ever take one apart? You'll actually see the blades in there with some supplemental spring steel pushing on the pins. That's why it's such a bitch to plug those things in and unplug it, because the outlet is just squeezing the snot out of the thing purposely to keep that resistance low. But if that gets compromised here, you can have an issue. And even more so, what's the ohmic resistance between that ground pin and the physical dirt? You know, it kind of makes all of our testing somewhat moot. You know, if we've got a crappy connection here or a crappy connection there, it's just like the ground doesn't exist. It's not serving its intended purpose. This is the kind of stuff that we can't often see it because it's buried, but it's that kind of bond into the physical earth that's also crucial. Right, and that's all where we often separate our work from the facilities. Well, that's their issue. You know, if you ask facilities, do they check tension? They don't. Nobody does that. But really, that's a piece of electrical reality, though, that is often ignored. That's why you don't want to do that. We don't do that, right? But your dads may have done that. Right? You don't need that thing. You'll cut that in on it when the plug is in the stretch, you know. But anyways, you don't want to do it. Anyway, we've got a couple other laws from guys you may have heard of. Ohm, George here, and we named resistance after. This is what I like about these old guys, and that's why I often have them included in here, because I want our students especially to appreciate and give some honor to these guys, these old farts that came up with this stuff. These are hundreds of years ago that they came up with these relationships. And again, you know, it's unlike software where that crap will mutate every 6 months and you got to learn a new language, right? You got C++ and Python, and you know, well, this stuff isn't going anywhere. So once you get these concepts down, like you got them for genetically ever. They're not going anywhere. But these guys, these laws further dictate everything about leakage currents, where we're ultimately heading. And the basic one of all things, Ohm's law, again, just incredibly elegantly simple, just simply describes the relationship between current, voltage, and resistance in a circuit. Current is equal to the voltage divided by the resistance. And the other thing is, it's a linear relationship, meaning if we double the voltage, you know, for a fixed resistance, we're going to double the current. And so it's a very elegant, very straightforward, very clean relationship, but it's at the root of everything we do electrically. I mean, none of the stuff we have could not be designed and determined and developed without these fundamental principles. That's for DC, with the DC batteries. The same law and the concepts are exactly the same when we're dealing with AC, things that we're plugging into our wall outlets. Now, instead of R, we refer to the opposition to flow in terms of what we call impedance. It's also measured in ohms, but it gets a little bit more messy now, a little bit more complicated, because impedance now may not only include resistance in the circuit, but also the effects of inductors, coils of wire, motors, valves, and also capacitance. We'll see. So anything we plug into the wall, anything, whether it be a light bulb, vacuum cleaner, electrosurgical unit, as far as the outlet is concerned, is going to look like one of these three combinations. Either it'll look like a pure resistor, or it'll look like a resistor and a capacitor, resistor and an inductor. In other words, the wall outlet doesn't know all of the stuff that happens to be in the box that's plugged in the wall. Another way of kind of thinking about impedance I kind of liken it to as a form of frequency dependent resistance. So the resistance, if you will, offered by capacitors and inductors changes with the frequency that happens to be associated with the source. And we'll see how some of this coming back to you from way back, like way back. Are you liking it now? Is it like you hated it at the time? But that's why I tell the students, I say, you got to embrace this stuff and make it your friend instead of an enemy that you gag at. But anyway, this is impedance can be purely resistive, which is exactly what we have with an incandescent bulb, a coffee pot, a space heater. It just looks like a resistance. And from an AC perspective, what that ultimately also is associated with is that the current, remember we've got an alternating voltage, right? Ohm's law dictates that we're also going to get an alternating current, I is V over R. And in a purely resistive AC circuit, the current and the voltage are what we call in phase. So as the voltage goes through zero, the current goes through zero. Voltage hits a peak, current hits a peak. They're in phase with each other. If we get into a little bit more complicated devices like motors, loudspeakers, solenoid valves that have a coil of wire in it, anything that has wire in it, coil like that also has a property called inductance. And the fundamental property of an inductor, that's what this coil here, L, I don't know why we call it F. The units are in henries after another guy, Joel, but I don't know where we got L, frankly. But anyway, the property of an inductance is to oppose rapid changes in current. So the current through an inductor cannot change rapidly. And that's precisely why the current in a RL circuit, a resistor inductor circuit, lags the voltage. So there's what we call a phase shift that exists between the two. And where I'm going with this ultimately, we'll see, is that just by looking at these two waveforms on an oscilloscope, we can determine whether we have an RL circuit predominantly or an RC circuit predominantly, and we can actually determine the values of those equivalent components. And we're going to get to that in a minute too. And that phase shift here, it varies from 0 to 90 degrees. It won't be never more than 90. So in some amount of shift here, we represent that by that Greek theta angle. A couple things on capacitors, and we'll see this is where we're getting to where leakage current comes from. But a capacitor, if you recall, it's a passive device. We don't have to put anything into a capacitor to make it work. Just the sheer physical nature of the device is what gives it its capacitive properties. And fundamentally, a capacitor is anything that has two conductors separated by an insulator. And two conductors separated by an insulator, and we have this property called capacitance. There's a little symbol here. So, and this is just a metal plate connected by an insulator that we call a dielectric. And it can be air. Remember some of our old stereo or FM tuner radios, they had variable capacitors in there that you used to change the frequency. And they were just a series of aluminum plates that we could vary the area of the plate, and we vary the capacitance, tune in different stations. Okay? Two conductors separated by an insulator is a capacitor. And what that ultimately tells us is that wherever we have capacitance and a voltage, X sub C is simply a term we use to describe the ohms, the resistance offered by a capacitor. Capacitive reactance, we call it. Technically, it's also in ohms, same thing, but it's also now determined by the capacitance and the frequency. And what this formula tells us basically is that as the frequency goes up, X sub C goes down. It's inversely proportional. So at real high frequencies, that capacitive reactance for a given capacitor can be very, very low. You ever had any dental work done like with a hypercator, like in the dermatology offices. They're basically small electrosurgical units that don't have a ground pad. You ever see those?
Yeah.
You just sit in the chair and with only one lead, they can cut your gums off. And why they can get away with that is because of the sheer capacitive coupling between your body and the chair you're in, and ultimately the ground and the instrument. There is capacitive coupling. There's capacitance right now. In fact, as we're standing in this room, there is a capacitance between my head, bald heads even get more maybe, and the electrical ceiling up there. There's a coupling we have between us and the power. But key thing is this is a form of Ohm's law as well. So this is just ohms, volts divided by ohms will dictate a current. And this stray or parasitic capacitance that we call it is precisely what gives rise to our leakage currents. The sheer proximity of conductors in a box. Even though you got insulated wires next to each other, we have capacitance. Between the hot side of the line and ground, neutral and ground, hot side of the line and a case, that's what gives rise to our leakage currents. I'll see a little bit more of this in a bit. Okay, so they're just byproducts. They're simple byproducts of any AC line operated device. Just by the sheer way in which it's constructed. I don't know if any of you guys, you might remember the old, I don't even know if we see it anymore, but there's a company called Dale. They used to have big blue line cords. You ever seen that thing? Big honking line cords. They were, I don't know about size, you got 5/8. I mean, real thick honking things. And this was back in our stupid days when we didn't quite know about what we were doing yet. But if you took the line cord apart, you would see these big polypropylene insulators in there. Okay? And why they came out with that is because it would reduce the leakage current in the cord. If you next time you get your safety analyzer out, just take an unterminated line cord, plug it in the analyzer, measure the leakage with nothing connected to the cord. You'll probably measure 5 to 10 microamps of leakage. Back in our early days, we were freaking out over 10 microamps. Oh, because it would fibrillate dog hearts, and we thought we were killing people with 10 microamps. We'll come back to that, but that's the kind of extremes that we went to as a profession back in the early days, coming up. And now if you ever tried to work with that crap, trying to put a new plug cap on it, I mean, it's like dealing with a garden hose, I mean, it's just a big pain in the ass, necessary acts to deal with that stuff. But that's the fundamental cause. It's this stray, and you might not even have a physical capacitor. We can, but you don't necessarily need to. Even at our transformers, you got conductors separated by an insulator. You got a capacitor. And this is even especially our line filters, RF filters in our devices. If you ever measured a leakage on a device and the leakage current was out through your roof, what the hell is going on? And the reason is that many devices will have a line input filter that has physical capacitors in there, not just parasitic, but physical capacitors between hot, case, neutral, and ground. And the purpose of those filters is to filter our incoming power line, which I don't know if you ever got to really look at with more sophisticated analyzers, especially in our hospital environments. We got all kinds of shit right now in our power line. That we think it's, pretty sine wave. If they got high-speed analyzers, if you really look at your power, you'll see all kinds of garbage right here. High-speed transients. I mean, you can get, nanosecond, sub-microsecond pulses on there, big honking spikes, fuzz and garbage, and that can wreak a lot of havoc with our sensitive, wussy microprocessor stuff. But anyway, these filters are designed to help try to filter some of that crap off, as well as prevent junk that our boxes, our devices might generate. We don't want to push that crap back onto the power as well. So some of your devices will have these filters in it, which have deliberate capacitors in there to do the filtering, and that will give rise to a lot of leakage as well. But how we can determine what those circuits look like is we can now look at the behavior of a capacitor is that it opposes rapid changes in voltage. And so what we see here is that the current will lead the voltage in a predominantly RC circuit. So just an example, if we had 10 nanofarads, 10 to the 10 billionths of a farad, 10 to the minus 9 farads of stray, or even a physical capacitor. You can do this. You find a small little capacitor in your toolbox somewhere. Just stick the capacitor value in here. So 1 over 2 pi, F is the frequency. The value of the capacitance in farads. So you got to keep your units straight. You'll get the amount of reactance or ohms. In this case, it came out to 265 kiloohms of resistance. So at 60 hertz, a 10 nanofarad capacitor, whether it's a physical capacitor or virtual or stray, is going to look like a 265 ohm resistor. Ohmic. The current that will then be allowed and forced to flow through that virtual or physical capacitor is again dictated by Ohm's law, 1V over R or Z here. So that would give rise to 452 microamps. So next time, if you gotta make sure it's a properly sized, the working voltage is large enough. Next time you have your safety analyzer on, get a small capacitor. Do the calculations first so you don't blow your meter up. But just stick the capacitor between the hot side and ground. And that's what you'll measure. Okay. And again, what's funky about this is that there's no physical capacitor. It's just the sheer proximity of all of this wire hanging around inside our boxes. Just so you open something up. So you got your hot side coming into a power inlet here, black, sitting right next to the case. Nothing wrong with it. I mean, it's well insulated. So you're not going to blow a main fuse or a break or anything. You're not going to kill anybody. But there is capacitance between that hot conductor and that case. Current leakage. Does that make sense, kind of? Does that make sense? And what I also did, I took a Valley, in this case, I took a Valleylab ESU we had laying around. And if you measure the line voltage, nominally 120, and you looked at this on a scope, in this case, we're looking at the voltage across a 1K ohm resistor, came out to about 80 microamps or so. If you superimpose those on the same screen, you'll see we've got a current leading the voltage by some bit of time here in milliseconds that we can convert, little ratio, we can convert that time in milliseconds to a degree angular phase shift in degrees, and we can basically get an equivalent RC circuit. What does the electrosurgical unit look like electrically? And what it looks like electrically is a 155 k ohm resistor in series with a 1.8 nano capacitor. So in other words, your safety analyzer does not know the difference, whether it's plugged into a medical device or if we just had a simple RC circuit connected to it. It's going to read the exact same thing. But this is just using this to kind of illustrate the source, the origin of these leakage currents. Again, not going to do this kind of crap on a day-to-day basis. But the more we understand where this stuff comes from, I think it puts us in a much better position to understand what we're doing. In fact, it was probably the first, God, I bet you 7 to 8 years or so. Many of our departments, if you don't have it, probably gave birth, were given birth to because of this leakage current stuff in the early 70s. First place I was at, they started the department because the Joint Commission was all over everybody, about killing everybody, electrocuting everybody. And it took Amy a good, I bet you 7, 8 years or more to come up with a standard finally on how we're going to measure these leakage currents. And actually what we're doing is measuring, there's a more sophisticated version of this, but at 60 hertz, the standard test load looks like a 1K ohm resistor. We're just simply measuring the voltage across a 1K ohm resistor to display our current in microamperes. So millivolts, in other words, divided by K ohms gives you current in microamperes. That's where it comes from, that the electrical stuff. How electricity affects our body is also basically fundamental. One of the first things is that you have to be part of the circuit, just like any DC or AC circuit. If there's the only way a current is going to flow is if you have a complete circuit. And whether there is a human being in that circuit or a light bulb, LED, and a resistor, bottom line, you have to have a complete circuit. The human body has to be part of that circuit if there's any current that's going to flow through it. And the other thing we obviously need is a potential difference across that circuit. There has to be a voltage difference in order to have a current flow. Ohm's law is V over R. If V is 0, I. The other thing we probably appreciate is that the physiological effects, how we respond to that, is based on current, not voltage. We've all gotten static shocks, in the wintertime, you get a metal doorknob or something, and you can have 10, 20,000 volts there. But the current is so small, that's why you don't die. The current is what causes the ultimate damage. And the three physiological effects is that you may get stimulated. This is what tasers do. You may get a shock, you get a startled reaction. And if it goes up in magnitude, I squared R. Back in the dorm days, students, they were cooking hot dogs. They just plugged two ends of a line cord into a hot dog, plug it into the wall, cooking the hot dog. I squared R. So you just resistive heating. This is what happens when we electrocute prisoners too. Hours after they're dead, their brains are in 100+ degrees. I mean, they just get literally cooked to death because of the incredibly high currents that are being passed. If they get really high, they can, blindmen can get the roots burned off. But fundamentally, what we see, and this is a bit old diagram, and the data, the numbers are a bit old, but the concepts are the same. At the lowest level down here, we have what we call the threshold of perception. And we'll see here in a little bit that the actual threshold for most of it is much, much lower. This is the smallest amount of electrical current that we can just barely perceive. You just get a slight tingle where you just perceive that little shock is the threshold of perception. If we go up a little bit more, and actually it's in the range of about 7 to 10 milliamps for men, 5 to 8, somewhere in there for women. That's the let go threshold. That's the threshold at which you see the Arnold Schwarzenegger guys, you're grabbing on the conductors. And if we get in that 7 to 10 milliamps, arm to arm, you cannot let go of the conductors. Physically cannot do it. Because the forearm finger flexors, the muscles in our forearm that control grip, are stimulated so much that you cannot physically let go. That's why our ground fault circuit interrupters, in the bathrooms and our wet areas, they trip at about 5 milliamps. That's designed and set that way to trip before we hit let go. So again, you could be butt gas naked in the bathtub, throw a radio in there. You might get a little tingle, but you won't die. And of course, if we go up, now we're going to start involving respiratory, intercostal muscles, breathing, heart. So, but early in that threshold is the key. A number of years ago, I always had difficulty trying to explain to students what is a microamps. They look at you like, what is he talking about? It's like, where's Pluto? How many blocks away is Pluto? It was such an abstract concept that they had no clue. So I made a stimulator here that they could put their fingers on, and I just have them turn up a knob till they feel the tingle. In fact, the very first generation of this, I did some guest lecturing in Mexico, at Chihuahua. And I had literally a black box with an AC milliamp on it, cords hanging off it. And just to mess with the TSA guys, they put it in my carry-on. And of course, I just wanted to see kind of what they do. I mean, it was kind of cool, but I just kind of was curious. And of course, it goes through the scanner, and they all hell breaks and sort of what the hell is it? Because it's literally a black box, no labeling on it, wires coming off of it. And of course, they pull it out of the box and they start yelling at me like, "What do you got here? What is this? What is this?" Jesus Christ, chill out. I'm not, But anyway, I started pointing at the boxes. We'll take the screws out if you want. So look in there. Get your hands away from there. And so they swabbed it all down. Because how am I going to say it's a 60 hertz electrical current stimulator? But anyway, I made a newer version of it. And the whole point of this is that you can put your fingers on here and you dial the knob until you just feel the tingle. And that tingle is your threshold of perception. Okay? And in this case, 176 microamps, you would not, maybe you wouldn't feel anything. And why that fundamentally is, this is all based on physiology now of our nervous system, our nerve cells. And I don't know, you guys had biology maybe somewhere way in the back? You remember maybe all cells, especially our nervous cells, neurons and receptors, basically have a resting membrane potential associated with it. There's actually a voltage, a measurable voltage between the inside of the cell and the outside of the cell. Measurable voltage in millivolts. And that resting potential is right around minus 70 millivolts. Minus 70 is on the inside with respect to the outside. So the cell is just kind of hanging around, not doing much of anything. And we start to stimulate it. Again, this can be chemically, electrically, photons, light, sound, touch. That membrane potential starts to change because of this external stimuli. And if we get to a certain point called the threshold, that cell will depolarize. So that the polarity shifts now from a minus 70 inside to maybe plus 20 or 30 on the inside, very rapidly. I kind of liken it to like a cellular orgasm. I mean, once that happens, there's nothing you can do. That cell is going to fire, and that's what a nerve impulse essentially is that rapid depolarization. And why that happens on the cell membrane are a whole bunch of sodium channels, selective ion channels. And I kind of think of this as like Walmart at Christmas time. You ever see all those 50,000 people out at Walmart? Right when they open up the doors, this flood of humanity runs into the store. Same kind of thing happens cellularly when we hit threshold. All these sodium channels open up. Sodium's a positively charged ion, floods into the cell, massively depolarizes here, and right around 20 or 30 millivolts, that's the signal, the solenoid now, shut the doors. We're kicking everybody out. And then the cell pumps all that sodium out. But the only time we're going to feel anything is when we get that threshold. The only time you hear anything, the only time you see a faint light, the only time you feel that mosquito crawling on your finger is when that threshold is exceeded. Okay? So by getting the students to feel it, oh yeah, now I got it, kind of thing, because otherwise before that, just a marijuana concept. Don't know what it's talking about. But anyway, all these nerves, all these receptors, you can kind of think of them as like transducers, and how the body basically decodes stimuli. These are these little action potentials, these little nerve impulses. And these are what literally is traveling down our nerves, just like digital signals down a conductive wire. These little impulses is each little depolarization. Okay? And it could be from anything. Okay? And how the body, the brain, decodes all of this stuff is by frequency. Okay, so the amplitude is fixed at about 20 or 30 millivolts, but the frequency is dependent on the intensity of the stimulus. So if you just lightly kind of stepped on a tack, brain's going, yeah, that's all right, do that. On the other hand, if you stepped on and slice your foot open on a piece of glass, holy Christ, that hurts like a bitch. The brain now interprets this frequency as intensity, a seriously intense stimulus. And these pulses literally are traveling down these nerves. What I used to do, I still do with the students in the freshman class, other classes, we do a little experiment with the guys and the women on where their mean thresholds are, and consistently, and I don't know this for sure, but it's a strong suspicion. The women in the class always pay attention. They follow the rules. I tell them, okay, now as soon as you feel the tingle, let us know. Okay. They follow the rules. So this is a standard error bar. So it's a measure of spread within the class. Relatively small. Mean about 241 for the women, 258 for the guys. You notice the guys have a much larger variance here. Again, I don't know for sure, but I just always see it. Guys are trying to be the macho. I don't feel nothing. I'm going, shit. 500 microamps, and they're saying I don't feel nothing, trying to be cool. So it screws up the data. Now you got, but anyway, these are these these thresholds here. Okay, pretty low. Anyway, all of this is leading to where you may have heard about this in 1971. Ralph Nader came out with this infamous paper that quite literally started our whole safety movement in a lot of ways. He's given kind of goofy credit for starting this whole thing, where he claimed we were electrocuting about 1,200 people a year in our nation's hospitals. And people got, holy shit, we can't be having that. And people got all excited about this, when in fact, he wasn't the first. The guy who first started this whole crap, a physician, Carl Walter, in '68, he's the one that came up with the 1,200. And it was just, well, I think I had one patient that did this, and we've got 1,200 patients, hospitals in the country. It was just completely pulling it out of the air somewhere else. But this guy, he invented blood bags. He was a surgeon at Harvard. He was a really well-renowned dude in his day. He was on some NFPA committees. He invented the first blood bank. You know, so this guy was no dope. So he had a ton of credibility with him. He came out with saying this. Unfortunately, ECRI was coming out at the time. I don't know if you know Joe Noble. He used to be the first president. He came out in '73 saying, you know, we got a mess going on here. And basically, the codes and standards were all developed to help the industry out. And so we've got equipment. You get the low leakage cable, hospital grade receptacles, plugs, all this stuff kind of was given birth from a whole bunch of real fuzzy, phony data at the time. We just didn't know. But people were scared to death of all of this stuff. And this is the scenario that started the whole thing. This is where Ralph Nader was coming, Walter was coming. This was published in an IEEE journal. And this was given, you know, these were all really well-respected people at the time. They were no punks. And the scenario, which was a whole lot more realistic in the day. So you got a patient here in a bed, electric bed. You remember the older beds, virtually all metal. Guardrails were all metal. Electric bed. The old electrocardiographs in that era, it was not uncommon. The right leg was ground, earth to ground, or very, very close to earth to ground. And the patient had an indwelling cardiac pacemaker cap, a wire right into the heart, coming out into a box. Yeah. So the scenario was, and that would not be atypical back in that era. Got a patient in a bed, external pacemaker hooked up to the ECG machine. You got a bad ground in the bed. Okay. Not at all uncommon, beds, bad ground. And so what happens, the leakage current now is available on the frame of the bed, because there's no place for that leakage current to go. So it's floating around, available on these rails of the bed. You have a nurse tending, leaning on the guardrail, making contact with the indwelling cardiac catheter into the heart. That leakage current from the bed, below her threshold or his threshold of perception now, can't even feel it, passes through the nurse into the patient's heart, through the right ground, bam, kill the patient. Electrocute them, dead. You know? And so people are, holy, you know, that's how people got nuts. But that was the scenario. You go back and look at the original article. I graduated in the mid-'70s, and I was flooded with this kind of stuff. I left school scared to death of these damn things. I started out, before I started doing some graduate school, as a tech in a local hospital. No, Gene. And, you know, a little monkey right out of school, didn't understand nothing about it. I was scared to death. I cut the plug once off the treadmill. I was doing some check on a treadmill, and I don't know what the leakage was. It was some ridiculous thing. Oh, I took the dikes off. I cut the plug off the treadmill. You know, saving mankind. And of course, I got my ass ripped because they had stress tests all lined up. Test plug out. You know, and I was on a mission from God, you know, to save the planet. But I didn't understand any of this stuff back then. It was just the fear at the time. But that's the scenario that started all this. There was a ton of research that was out at the time. Geddes and Baker, really well-renowned people. I mean, you know, they were doing all kinds of studies with dogs, but all we knew is that, you know, 10, 50 milliamps with big fibrillate, microamps with fibrillate dog heart. So we just simply extrapolated that the humans are more valuable than dogs. So that's how these ridiculously low original leakage currents came from. And it was almost impossible to read. That's why the line cords came up. Isolated transformers, all kinds of stuff, trying to keep it safe. But this is where I ultimately wanted to get to. This is the whole point of all of this ramble, is to get to why what we have to have in place before we're going to shock anybody. Whether it be a macro shock, arm-to-arm, external, or a micro ingoing catheter, there's 5 things that all have to be present in order for we have any risk at all. 5 things. Okay? First thing, we have to have some conductive case, a conductive case on our devices that is capable of being energized, electrically energized from the inside. So you got to have a conductive case, first of all. So this automatically throws out anything that's double insulated, either a UL double insulated or effectively double insulated. Conductive case that can be energized from the inside. How many conductive cases do we see around anymore? I mean, they're still out there, obviously. And some of them, the only reason they put a conductive stud on there so you can do our stinking measurements. But there's nothing conductive on many of our devices that is capable of being energized from the inside. That's a key. The second thing we need is sufficient coupling, that RC coupling between the hot side of the line and the case. Okay, so we have to have sufficient, there has to be, if you have coupling that's only going to give you, 10 microamps of maximum leakage current, that's not sufficient. You'd have to have sufficiently high capacitance, low resistance to cause sufficient coupling to that conductive case. Second. Third thing, and again, it's that impedance here that determines that coupling. Third thing we have to have is a defective ground, either from the case to the plug, from the plug to the outlet to physical earth, defective ground. We've got an intact ground. Frankly, we don't care what the leakage current is. Back in the day, I don't know where it is quite now, but lab equipment, we were still trying to do all of our safety stuff on lab equipment. If you ever tried doing that back in the day where they got things stabilized and calibrated, you're going to go in there and unplug all their equipment and screw up all their they're not going to allow you to do any of that. And especially for devices that were semi-permanent, I was putting redundant grounds on. So and I just used that as my argument. I'm not doing that test because I've got a redundant ground in there, and it doesn't matter what the leakage current is if you have an intact ground. That's the third thing, defective ground. And again, verifying this still remains a very legitimate test to keep doing. And frankly, where I'm at right now here is I'm arguing that's more of a valuable test, more important than human leakage current. Ground integrity is important. It's not just from a safety standpoint. There are certain filtering things that's also unique benefit from having the intact ground. Why the intact ground is so protected, it comes from Kirchhoff's current law. If you remember that from somewhere, the sum of the currents entering a node have to equal the sum of the currents leaving. It's from that fundamental law and its relationship between a total current and how that current divides. Just like water in a garden hose. If you got a Y in a garden hose, water comes in, whatever comes in has to go out. Same thing with current. Whatever total current flows in, the sum of I1 and I2 have to equal IT. And this is why, from that fundamental law, why the ground is protective. If you've got a 0.5 ohm of a ground resistance versus say 1,000 ohms, which is a low resistance for a human, 1,000 ohms of Joe Person here, Kirchhoff's current law will tell you and guarantee that most of that current, 499 out of the 500 microamps, is going to flow through the ground. Only a microamp is going to harmlessly flow through the patient. So that same concept, if this is 500 microamps or 5 amps, the concept's exactly the same. Most of that is going to flow through the low impedance pathway as opposed to Joe Person. Fourth thing we have to have is you have to have Joe person or nurse, staff, patient, whatever, has to have a reasonably low impedance connection between that exterior case or some point on that device. Then they have to be part of the circuit. Remember, like that very first slide we had, in order for any current to flow through a human being here, they have to be physically, electrically part of the circuit. So not only do they need a low connection at the box, the device, but they also have to be grounded. Again, reasonably low impedance, because Ohm's law will still dictate how much current eventually could flow through everybody. There were some cadaver studies early on that said even under this worst case, from one arm to the leg, only about 10% of any currents that were being passed through the body would pass through the heart. Not that we want to do this, but in other words, there's a lot of shunting going on within the body. So even though you had 500 microamps flowing in from one arm to your right leg, out of your right leg, doesn't mean all 500 is going to go through the heart. It conducts more through nerves, other pathways. You put all this together, you remember your Boolean logic? AND gates? A and B and C and D and E. So all 5 of these things ANDed together have to be present in order for we're going to get an output. We're going to get a shut. 5 things. And some basic probabilities. Simply, and this is we don't know what these actually are, but the point is that a probability is a measure of chance. We score from 0 to 1. At a probability of 0, totally, absolutely impossible for something to happen. Probability of 1, absolutely certain it's going to happen. So we have it's a continuum all the way, anything between 0 and 1. Classic example: you flip a coin. Right? Chances of getting a heads, 50%. If you the chance of getting 2 heads in a row, because these are independent events. Right here, your second coin toss has no bearing on the first coin toss. 2 independent events. So the probability of a heads times the probability of a heads. The chance of getting 2 heads in a row, 0.25. Chance of getting 3 heads in a row, you multiply these independent probabilities, 0.12. Probabilities keep going down. Okay? What that also means, because these are what we call a compound probability, independent events, if we reduce any one of these to 0, anything multiplied by 0 becomes 0. So any one of those 5 things, if we eliminate it, the whole thing goes to 0. Meaning the whole risk of getting any kind of shock goes to 0. And again, this isn't opinion. This is just the way this crap works. I mean, I didn't invent it. I mean, it's just how it behaves, right? So bottom line, absolutely keep doing your line cord inspections. This stuff gets ground up all the time. Obviously, plug caps, spring release, all of that's still good. Ground cord resistance, still a very good thing to do. And I'd even though you want to put it off on the facilities, just get one of these little simple fish scale kinds of things. And most of the time, especially with hospital grade receptacles, you don't have to worry about that. Those things are almost dead on forever. I mean, they get supplemental spring steel in there. But don't forget it. Then bottom line, I don't know if your management is going to allow you to do it. I won't mention who, but I did this at a presentation once, and one of the managers from one of the big shared service groups, I asked them, are you guys still doing routine, leakage currents? Oh yeah, we have to. Even though they kind of think, I don't want to do this crap, the management, and especially for an ISO, you got any ISOs in here? Mm-hmm. Well, nothing against you, but safety sells, right? So when you're out there selling safety, people will buy that. And, but again, there's so much more we can be doing. There's so much more we can be doing. In our early days, it was not at all uncommon to have safety testing essentially synonymous with PMs. We didn't give a shit if the defibrillator worked, but the leakage current was less than 100 microamps. They were verifying that stuff. But the things that we should be paying attention to, kind of letting go. So even though it's blasphemed a little bit, this is kind of how it all also. So it's just stuff to chew on, think about, take it back to your places and think about, because if you think about the number of time collectively as a society and as a profession, You got thousands and thousands of devices, even though it might take you 30 seconds to do a stinking leakage current. You got to punch it in the CMS somewhere. You got to record the thing. Either you did it or you didn't do it. And how many times have you been out there measuring and they don't change? Or it doesn't. And it can. I mean, there are legitimate things that can cause leakage currents to go up. I mean, the centrifuges I've seen, that graphite does. There are, moisture and urine and puke and everything in there. And there's all kinds of things that can screw up and increase the leakage currents. But again, if you have intact grounds, all that stuff, you're killing people. Make some sense, kind of?
Yeah, you bet.
Okay. Well, thanks for being here.
All right.